Is Yuzhi Cai from the Wharton Business School, and he's going to be talking on large-scale multiple testing, finding needles in a haystack.
First of all, I want to thank the organizer for inviting me. It's great to be here. The Institute in particular is a great place. So the topic of my talk is slightly different from the talks.
Switch on.
The topic is slightly different from the talk we heard so far today, and it's on multiple testing, and it's joint work with my PhD student, Wenguang Sang. And here's a brief outline. I'll begin with some general introduction on a few large-scale inference problems that's slightly different from the regression problem we have heard so far. And then I'll focus on the testing problem and treat the multiple testing problem as a compound decision problem. And then if we have time, I'll discuss the some theoretical results as well as some numerical results. And then towards the end, I want to discuss a slightly non-standard problem of testing grouped hypotheses, where you have many, many hypotheses, but they're grouped. And as evidenced by many, many examples we have heard so far, that there are many, many problems in application that involves large data sets, and the signal is very sparse. And for testing problem here, we want to find the signal, the location of the signal, which observations contain signal and which observations are noise. Or you can think of this as gene, and which genes are significant and which genes are not. So this kind of problem can be generally viewed as finding needles in a large haystack. And there are many, many examples, and I want to mention in particular this example in astrophysics, and which John Rice is going to discuss in much, much more detail on Friday. It's a very, very interesting problem, both statistically and scientifically. And I'll mention a little bit more later on. And in all these problems, we need to do a large number of hypothesis testing, like thousands or millions simultaneously. And we want to control the overall error. And in these problems, it's convenient, and also it's very effective to use a two-component mixture model. We think that the observations with certain probability coming from the null distribution, the background or noise distribution, and with certain probability comes from some alternative distribution or non-null distribution. And given the data, we want to know whether x comes from the null or x comes from the alternative. And in this case, we also have this parameter p. It turns out that p is very interesting by itself. Like in this example I mentioned here, actually p is the main focus. We want to know what proportion of the observations come from the alternative. And a collection of problems that's interconnected. The first one could be test whether p is 0 or not, whether this haystack contains any needles at all, or whether there's any signal at all. So we want to test whether p is 0. So you can think of this as testing a global hypothesis. And assuming that p is not 0, for some problems like the one I just mentioned, we want to estimate the fraction. Which fraction of the observations comes from the null, which fraction comes from the alternative. And also we will see that estimating the fraction, this p, is very, very important for the next problem, which is multiple testing. In multiple testing, not only we want to know whether the haystack contains needles or not, we want to know where. Where are the needles, or where are the signals? And the next step could be, say, estimation of the signal itself. How large is the signal? You can think of that in general terms as a regression problem. We want to estimate the signal. So the main focus of this talk will be on the third one, but I'm going to mention the other two briefly first. It turns out the problem is very interesting even in the simplest setting. where we have a two-component Gaussian mixture. So we assume that the observation with certain probability come from the null, which is normal 0, 1. You know it. The null distribution is normal 0, 1, and with certain probability come from normal mu 1. So in other words, the mean, if it's not 0, it's mu. The problem is not that interesting if this p is large or p is a fixed constant. It's only very interesting if this p is very small, especially this p is n to minus beta, where beta is greater than 1/2. So it's very sparse. If beta is between 0 and 1/2, the behavior of the problem is totally different. And we will not get into detailed discussion of that. And in that case, if p is very sparse, we should calibrate this mu n in terms of this r, square root of 2r log n. And we ask the question, when we can tell it contains signal. So that's a detection problem. Is there any signal at all? And that problem was considered by Inster and as well as in Donahoe and Jing. And once you know that p, you reject the null hypothesis that p is 0, then you want to know how large p, what's the value of p. So you want to estimate this p, and that problem was considered, the consistency was considered by Manshausen and Rice, and also in two recent papers by myself and Jiasun Jing, who is here. And it's also interesting to look at this in some abstract way. This beta itself is an index for sparsity. The larger the beta, the sparser the signal. So as beta goes from 1/2 to 1, the signal becomes sparser and sparser. And this r is an index for the strength of the signal. As r goes up, the signal becomes larger and larger. And turns out that there's a very interesting detection boundary, which is a curve. Below this curve, you have no way to tell whether p is 0 or p is not 0. It's not detectable. You cannot test the global hypothesis. And once you're above this curve, it becomes detectable. Asymptotically, you can tell that it contains signal. But what's interesting is that if you are in this white region, although you know this haystack contains needles, there's no way you can tell where. Only when the signal is strong enough above this straight line, then you can classify it. It means that not only you know p is not 0, you can also tell which coordinate is not 0, or which x comes from the null, which x comes from the alternative. And as I said before, that when it's above this curve, you can estimate. So here, in terms of estimation of the fraction, as soon as you can test, or you can tell p is non-zero, it turns out that you can estimate p. Not only you can estimate p consistently, you can estimate p as optimal rate. Now let's go to the multiple testing problem. In multiple testing, we want to know where the needles are. So we have a collection of hypotheses, and associated with each hypothesis is a test statistic. We can think of this kind of setup where we can think of this as subject. x1 is subject 1, xn1 is subject n1, and this can come from, say, the disease group, and the y's come from the control group. And for each gene, we can measure the expression level, and for each gene, we can calculate the summary statistic, for example, a t-statistic, or we can convert the t-statistic to a z-value, or we can compute the p-values. So from the rest of the talk, we are going to focus on the z-values or the p-values as a summary statistic. And what's the goal? The goal is try to determine which gene comes from the null, which gene comes from the alternative, or which gene is differentially expressed. And we assume that under the null, if the null distribution is true, if null is true, then the test statistic, Sj, has a null distribution, a common null distribution. And then no matter what you do, for any procedure, we can summarize the result by this table. You either do it right when the null is true and your conclusion says it's non-significant, then you have made a correct decision. Or the truth can be non-null and you correctly claim it's significant. You also have made a correct decision. But it's possible that when the truth is null, but you claim it's significant, then you have made a type 1 error. So that's a type 1 error, and that's a type 2 error. And you can also take the sum, the total number of non-significant ones claimed by the test, and also the total number of significant ones claimed by the test. So those two are the outcome of the test, and M0, M1 are the truths. How many true null and how many true non-nulls. And it's clear that if you have a large number of hypotheses, like 1 million, the classical method doesn't work. If you use Banfaroni, for example, you're not going to reject. Most likely, you're not going to reject any, because it's way too conservative. And the false discovery rate is a very nice measure of that, which allows you to make some mistakes, but not too many. So this FDR, you can think of this as the false discovery rate. Among all the rejections, how many of them are false? And there are some related measures, that like positive false discovery rate or marginal false discovery rate. Asymptotically, they're all equivalent. So in this talk, we're not going to differentiate among them. And the dual quantity is the false non-discovery rate. Among all the hypotheses that you don't reject, how many of them are false? So the false non-discovery rate. And this is a measure of, say, type 2 error. And for FDR is a measure to control type 1 error. And the well-known BH procedure, the step-up procedure, is very simple and very easy to implement, and it's also very popular. And you can see here that it involves 3 steps, which is very simple. For each gene, you calculate the p-value. Then you have a collection of p-values, you line them up from smallest to largest. Then you threshold. You cut somewhere, and it gives you a specific thresholding rule. You cut pi at this line, and the last one, below this line, you reject all the hypotheses before that. And so it's very simple and straightforward. And also with a very clever proof that show that this procedure controls the FDR at this level. M0 is the number of true nulls, and M is the total number of hypotheses times alpha. So graphically, you can think of the procedure as this way. You line up the p-values from smallest to largest. Then you draw a line, and this line has slope of alpha. And then the last time it's below this line, you reject all the hypotheses. Then, and you don't reject the rest. If you look at this procedure, again, you will see that the true FDR level is 1 minus p times alpha by our notation. Then clearly, it over-controls. And you can certainly correct this if you know p. If you know this p, you can apply the BH procedure. Instead of this nominal level alpha, you apply this as a different level, alpha over 1 minus p. Then you multiply by 1 minus p. It's exact right. And here you already can see that the value of estimating p. You need to, because we don't know p. If you don't know p, you can estimate. So we need a good estimate of this p for multiple testing. Assuming we can estimate, then we can replace this p by p hat. And basically, that's the idea of the BH adaptive procedure and the plugging procedure by Genovese-Westermann, and those two procedures are equivalent asymptotically. So if we think about the multiple testing problem, so far there are many procedures, and most of them are based on the p-values, and the goal almost always on controlling the FDR level. But if we think about in terms of testing as a decision problem, certainly controlling the type 1 error is not the only goal. Because in the classical setting of a single hypothesis testing, we learned in the first course of statistics, we don't just want to control the type 1 error. We want to control the type 1 error. And among all the procedures that controls the type 1 error, we want to pick the one or construct the one that minimizes the type 2 error. And if it's simple versus simple, then Neyman-Pearson is the optimal procedure. And according to Efron, the Neyman-Pearson lemma is the single most important result in all applied mathematics of 20th century, for the whole century. And we can argue about that, but certainly it's an important result. So we can, in multiple testing, we can certainly try the same goal. Whether it can be achieved or not, it's another question, but we can certainly mimic this goal. We want to control the FDR level, and then we try to minimize the FNR level. And the solution is not clear so far, but that's the main topic of this talk, and it's a compound decision problem. And we will call an FDR procedure valid if this procedure controls the FDR level at a pre-specified value, say alpha. And we call the procedure efficient or optimal if it has the smallest FNR among all FDR procedures controlled at this level. So that's similar to the goal of Neyman-Pearson. And first of all, I want to mention the role played by p-values, because virtually all the procedures so far in the literature are based on thresholding the p-values. P-value, of course, is a very fundamental quantity in the classical theory. For example, if you have tests, you compute the p-values, you can compare the p-values with, say, alpha level, your significance level. If p-value is smaller than alpha, you reject, otherwise you don't. And because of, I think maybe because of that, in large-scale multiple testing literature, p-value continues to play a fundamental role. Virtually, as I mentioned before, virtually all the procedures, FDR procedures, are based on thresholding the p-values. And also the focus so far has been mostly on the validity of the procedures instead of the efficiency or optimality. So before I go on, I want to emphasize the main message of this talk, that our result shows that the p-value is not a fundamental building block in large-scale problems. One shouldn't based on the procedure on the p-values. And thresholding the ordered p-values does not in general lead to efficient multiple testing procedures, no matter where you cut. As long as you threshold the p-values, the procedure is not going to be optimal. And here's a simple picture. If we have, say, if the test statistic is a normal mixture, and the null is normal 0, 1, that's a null distribution. And 80% of them are null, and 20% of them are non-null. And among the non-nulls, it's either -3 or 3. So if a two-sided test, we look at the absolute value, then the p-value doesn't depend on, any p-value-based procedure doesn't depend on this p1. And for a given FDR procedure, the optimal procedure controls FDR level at 0.1, and the FNR level is a constant. It doesn't depend on p1. But in fact, you can achieve much less FNR with another procedure, the optimal procedure based on z value, which I will discuss in a moment. So in terms of the setup, I want to repeat again. We have the observations, and those are not the original observations. Those are z values or the t statistic. For each gene, we have a true state. Theta is either 0 or 1, either null or non-null. And we observe those x's. So we want to make inference about theta based on x. And we are going to use a two-component random mixture model. So the thetas are IID Bernoulli P. And given theta I, xi is either from the null distribution or from the alternative distribution. And the density of Fi is denoted, capital Fi is denoted by little fi. So the marginal PDF is the mixture. And the goal of multiple testing is we observe xi and we don't know theta I. So we want to make inference about theta I based on xi, and we want to do this constrained optimization. Given the FDI level is controlled at alpha, we want to minimize the FNR. So that's the goal. And we are going to solve this problem indirectly, because it's a testing problem. I'm going to begin with a very simple example due to Robbins, and it's back in 1951. And this example is very, very simple, but it's very, very instructive. And actually, Charles Stein attributed to this paper as the inspiration for his shrinkage estimation. So suppose we observe x1 through xn. Each xi are independent, either normal 1, 1 or normal minus 1, 1. So theta is either 1 or minus 1. They're known. Either theta is minus 1 or 1. And we are going to try to classify theta I based on xi. And we use, so it's a classification problem. We use a simple, this usual classification loss function. So it's a proportion of it's a misclassification rate. And the problem is very simple, so it can be solved very precisely. It's easy to show that the minimax rule is simply the sign of xi. If xi is positive, you classify theta I as 1. If it's negative, you classify it minus 1. And it turns out it's a unique minimax rule. And this is a simple rule. It means that theta I hat only depends on xi. You don't need to look at any other x. So the decision of the ith component only depends on the ith observation. And this has a constant misclassification rate. And one might be satisfied with this solution, because it's a minimax rule. Not only it's minimax rule, it's a unique minimax rule. You don't need to look at any further. So you cut right in the middle. But it turns out you can beat this rule sometimes significantly. Now let's think about an oracle rule. Suppose an oracle tells us something a little bit more. Tells us that each theta I is 1 with probability p, and is minus 1 with probability 1 minus p. Or in the deterministic setup, you know the proportion of 1s and the proportion of minus 1s. If that's the case, it turns out that you can compute the base rule or the oracle rule. And the oracle rule tells you that you shouldn't cut in the middle. You should cut somewhere else. And this somewhere else depends on this p. If you think about this for maybe 2 or 3 minutes, you will realize that it makes a lot of sense. But of course, in reality, you don't know p. But as we always do, if you don't know p, you estimate. And this p is very easy. It's easily estimatable because it's either minus 1 or 1. You look at x bar, and x bar is a simple function of p. And you solve that this p hat is 1 plus x bar over 2. And those are for extreme cases. In other words, we can threshold at a different t star, and this t star depends on x bar. So now the rule is no longer a simple rule. It's a compound rule. It depends on whether you classify theta I to be 1 or minus 1, depend on not only xi, also depends on all other x's. What's the performance of this? You can see that the original minimax rule has a constant misclassification rate. And this data-driven rule, when n is infinity, which is this base rule, is strictly below this line. For a finite sample of different n, you can see that you only lose something in the middle. But if the proportion p P is highly asymmetrical. So if P is either close to 0 or close to 1, actually you can beat this rule significantly. What that tells us is that one should utilize the distributional information of the axis, not only the marginal information. And we are going to use the general idea of this for the multiple testing problem. So instead of solving the multiple testing problem directly, I'm going to solve a weighted classification problem first. So, and also we want to solve this case first. Suppose an oracle knows this P, F0 and F1. So you know the null distribution, you know the alternative distribution, you know the proportion P. And based on the observations, we want to find a general decision rule such that this weighted misclassification rate is minimized. And this depends on this lambda. And suppose lambda is given in the setup for weighted classification, lambda is given. And turns out this problem, just like Robin's problem, can be solved quite easily. It's an optimization problem, it can be solved. And you solve this problem, it turns out it's nothing but thresholding the likelihood ratio. So 1 minus P times F0 divided by P times F1. And you threshold at 1 over lambda, and that's your lambda. So if you know lambda and know everything else, for a given observation, you know where to threshold. And that's optimal. Now, why we look at this problem first? It turns out that under mild conditions, multiple testing problem is equivalent to weighted classification. This problem is like a Lagrange, or this loss function is like a Lagrange function of the multiple testing problem. And the oracle test, the oracle testing rule at level alpha is of this form. So for multiple testing, we don't specify a lambda. We specify an alpha to control the FDR level. It turns out for a given alpha, there's a corresponding function of lambda of alpha. And then we apply this rule with lambda alpha. That will give us the optimal test. The only problem is that this function is very complicated. It depends on the distribution of that likelihood ratio. But before we go on, well, we should notice that this ratio is nothing but a monotone function of local FDR introduced by Efron et al. And but their motivation is quite different from what we have here, because after you reject the hypothesis using BH procedure or any other procedure, so you have a set of significant genes, you need to know which one is more significant than others. So this local FDR has a very nice Bayesian interpretation as a posterior probability of being in the null group giving the z-score. So it's a very nice interpretation. But our lambda of x is a monotone function is a strictly increasing function. So thresholding this lambda is the same as thresholding the local FDR. And not only that, there's some advantage of dealing with local FDR later on, because in the denominator, it's a marginal density instead of the density of the alternative. So from now on, we are not going to threshold lambda of x. We are going to threshold this local FDR. So in theory, if we know everything, we can find an optimal threshold lambda, which depends on this alpha, and the optimal test statistic is a local FDR statistic. So in theory, all is fine, except this guy is very hard to compute. Given alpha, it's very hard to compute this lambda. But it turns out that one can find an asymptotically equivalent procedure, which is quite easy to implement, is that for each x, we can compute this statistic, local FDR, assuming you know P, F0, and F. Once you compute that, you line them up as before. what you do with the p-values, from smallest to largest. Then you look at this cumulative average of this local FDR statistic. And this cumulative average, because it's increasing, somewhere it will pass alpha. And then the last time it's below alpha, then you reject everything before that point. So now everything is fine if we know everything else. If we know P, we know F0, we know F. But, so first of all, some remarks about this procedure based on local FDR. So first of all, the local FDR was originally introduced to provide a useful Bayesian interpretation for individual cases. But here we rediscover this as an optimal statistic for multiple testing. But what's more interesting, and also it shows why p-value is not good. An interesting consequence of using the local FDR statistic is that an observation located farther away from the null, i.e. a larger absolute z-value or a smaller p-value, may not be less significant, may be less significant. So a smaller p-value doesn't mean the corresponding observation is more significant. So it's possible that the test accepts a more extreme observations while rejecting a less extreme observations. Intuitively, it's not so obvious, but let me draw a simple picture. You will realize that why it's so. I'm going to take a very extreme case. Suppose under the null, it's normal, standard normal. Now, under the alternative, suppose that distribution is very concentrated, say, at 1.5. You have a very concentrated alternative distribution, F1. Imagine that you observe something around 1.5. Then it's more likely it comes from the alternative than from the null. On the other hand, if it's highly concentrated at 1.5 and you see something like 2, it's almost impossible that 2 is from the null, is from the alternative. So looking at p-value is not the right way of looking at the problem. And here's one example of this. Suppose we have a normal mixture, a 3-component normal mixture, with certain probability it's null, and with some P1 comes from mu1 and P2 comes from mu2. And as before, we fix the total proportion of the alternative to be 20%. And mu1 is -3 and mu2 is 4. And the marginal FDR is 10%. Then it turns out the rejection region, if we use p-value, the optimal rejection region is this, the absolute value of zi greater than 2.27. But for the optimal z-value based oracle procedure, it's non-symmetrical. The rejection region is non-symmetrical. If we look at here, what's the consequence of that? Is that if you see a z-value equal to -2, or p-value is 0.046, you reject. But on the other hand, if you see x equal to 3 and the p-value is much smaller, it's 0.003, you don't. So a smaller p-value doesn't mean it's more significant. It depends on the distribution. And if we compute the FNR level, you will see that as a function of p1, the proportion of -3, you can see that it's strictly below the blue line, which is the optimal p-value based procedure. Now, we have dealt with the ideal case, where we know P, we know F0, we know F. What in reality you don't know. But if you don't know, you estimate. So in practice, we don't know P, most often we don't know F0, which I will discuss slightly more on the next slide, and we don't know F1. So if they are unknown, but for the moment, let's assume it's estimable. They're all estimable. Then we can certainly replace those by the estimated value and compute this empirical version of local FDR. Then we plug in, and we do exactly the same as before. We line them up from smallest to largest. We look at the cumulative average. And the last time it's below alpha, we reject everything up to that point. And that's it. And if you have an estimate for those quantities, this procedure is clearly very easily implementable. And actually, we have R code on my website. It's easy to implement. And also, it's clear from this discussion the performance of this procedure depends on the quality of those estimates. If you have very lousy estimates, this procedure, this testing procedure is not going to do very well. But the question is, what if you have good estimates? It turns out that if you have good estimates of those quantities, then this procedure is asymptotically optimal. So the data-driven test procedure is asymptotically optimal, given you have reasonable estimate of P, F0, and F. So suppose P hat, F0 hat, and F hat, they are consistent. Then the adaptive procedure controls the marginal FDR at alpha asymptotically. And also the FNR level of this procedure converge to the oracle procedure, which is the optimal procedure, even if you know everything. Now the question is, how do you estimate those quantities? The estimation problem, which is an interesting problem by itself, but it's a separate problem, has nothing to do with this estimation problem. So clearly we either need to know or need to estimate those quantities. And for those problems, estimation of F, which is a marginal density function, is a standard problem in non-parametric inference. And there are many, many procedures like kernel estimate, wavelet estimate. So we are not going to discuss it here. It's well studied a long time ago. And it's new, relatively new for estimating P and F0. And F0 is somewhat subtle. And also, it's philosophical as well. The null distribution, for most of the problems, at least in the classical theory, we assume F0 is given, F0 is known. So when all the assumptions, theoretical mathematical assumptions are true, then this F0 is indeed known. For example, the z values or the p values should follow the theoretical null distribution, which is uniform. And the z value should follow a standard normal distribution. But on the other hand, empirically, Efron has argued very strongly that in many applications, the empirical null distribution is quite different from the theoretical distribution. And the whole testing outcome, the outcome of the testing procedure, actually is highly sensitive to the null distribution, which is not surprising. So he has argued very strongly that instead of using the theoretical null, one should use the empirical null. In other words, one should estimate F0 instead of assuming F0. And the estimation problem has, as I mentioned before, of both P and F0 has been discussed before. For example, in a recent paper in JASA, we construct a uniformly consistent estimate. And in a paper that's about to be finished, we look at the problem of optimal rate of convergence. Look at the minimax performance of estimating the proportion P and the null distribution F0. And turns out these problems, especially estimation of the null, has very strong connection to the classical problem of deconvolution. And both in terms of technique and also in terms of rate of convergence. In terms of rate of convergence, it can be very slow, like logarithmic, which is very strongly connected or similar to the deconvolution problem. Now, I'm going to skip some of the numerical results discussion. So let's look at one case. Suppose the z-values under the null, it's normal, say mu 0, sigma 0 square, and the alternative, it's a mixture. Here, it's not a single normal distribution, but a mixture distribution. It's a normal distribution convolved with something else. And if you take both location and the scale mixture of normals is dense in the space of all densities under L1 norm. So it's very general. And we are going to take the approach in the paper I just mentioned to estimate the null distribution. Then let's look at some numerical results. So in this case, we have seen this before earlier, where mu is symmetrical. It's either -3 or 3. Then the oracle procedure based on the z-value, the data-driven, the oracle procedure is strictly below the constant level because the p-value based procedure doesn't depend on p1 because you take absolute value. But even in the other situation where mu is not symmetrical, -3 and 6, it's always strictly below, and sometimes the difference can be quite significant. And I think I'm going to skip this, and this is our procedure. It's always below the p-value based procedure. I'm going to skip this. I want to mention very quickly about another problem. Now imagine that instead of a single haystack, you have multiple haystacks. Each one of them contains some needles or some signal, and you want to know where. And this problem turns out to be arises quite often in many applications. For example, if you have SNP data from multiple chromosomes and they have different behaviors for different chromosomes, or you have different haystacks, and also for, say, in imaging analysis, brain imaging, the front half and the back half of the brain behaves quite differently. For example, you can have different proportion of signal, and sometimes you have different distributions. Or in clinical trials, you can run trials at different location in different country, or you have different subpopulations. But at the end of the day, you want to combine all the data to do a meta-analysis. And it's obvious if you have multiple haystacks, because we know how to deal with a single haystack. You can either combine all those haystacks to build a big haystack and apply whatever method you have used before. That's one method, and that's a pooled analysis. Another one is you can apply your procedure individually to each haystack. And you can also do that. And in a recent paper, Efron has argued that pooled analysis is not such a good idea. And also, it's fairly obvious if you think about this slightly more carefully, because you can have different proportions. Also, you have different separations between null and the alternative. One shouldn't combine them together. So he argues for the separate analysis. But what we want to do is we want to look at this problem more globally. We want to suppose we have observations. Some of them come from the first group. Some of them come from the second group. Suppose we have k groups. And within each group, some of them are null and some of them alternative, and so on. So we have multiple haystacks, and each one has some needles in it. And we want to locate those needles, but we want to control the false discovery rate globally. We don't want to control individual one, because if we want to control the individual one, you can simply apply this procedure one by one. And this is one example from the brain imaging data. So if we apply that, whatever procedure, like the procedure we have just discussed earlier, we can certainly pull them all together to have a big data set and apply that. And we can do that easily and look at this procedure. And Efron, as I mentioned, that Efron argued that pooled analysis is not good. Or you can apply this procedure separately for each group and say each one at level alpha. And this is a valid procedure, so is this one. This one, it's obvious it's valid because you only have one giant data set. And this is also valid. The overall FDR level is controlled at alpha. It can be shown very easily if you control each individual group at alpha. But it's also fairly obvious that one shouldn't apply this procedure for each group at the level alpha across all individual groups. For some group, you should use, say, higher alpha. For some other group, you should use lower alpha so that overall it's alpha because that's your only goal. But it's not obvious at all how to assign those alpha k for each individual group. So we are not going to do that. What we are going to do is we are going to apply a procedure. It's called conditional local FDR. That's sort of global, but sort of local. And we compute, by the way, it's the optimal test statistic. One can show that. The optimal test statistic is for each individual group, we compute the local FDR statistic like before. But once you have made the computation, you don't threshold them individually by each group. You combine them together. So you combine them together and rank the conditional local FDR all together from smallest to largest. Now you apply this cumulative average. It turns out it can be shown this is the optimal procedure. And not only that, and we show that this is more efficient than both the pooled analysis and also more efficient than the separate analysis. And as a byproduct, as a benefit, that's for free, you can compute or you can estimate using this procedure, the estimates the corresponding local FDR, the FDR level for each individual group. And here's one example of that. And overall, let's see, that's the pooled analysis, and that's the separate analysis, and this is the conditional analysis or the optimal analysis. It has smallest FNR. And in some other setting, actually, those two crosses each other. It means that one doesn't always prefer the pooled analysis or the separate analysis. Sometimes the separate analysis is better than the pooled. Sometimes the pooled is better than the separate. But both of them are dominated by the optimal procedure. And this is, in this simple example, we can compute the actual FDR level for individual groups. This is an example with two groups. If we look at here, you can see that in the first group, the actual FDR level is about 5%. But for the other one, the FDR level increases from almost 0% to about 10%. So you don't assign the same FDR level for different groups. You should choose them differently. But of course, empirically, it's very hard to do if you want to play that game. So as a conclusion, that the p-value is not a fundamental building block in large-scale multiple testing, the local FDR is. And thresholding the ordered p-value does not, in general, lead to efficient multiple testing procedure. And we set up the problem in this compound decision theoretical framework, and we derive the optimal data-driven procedure. And inspired by the title of this workshop, I add this slide. The future direction is a dependence case. With dependence, the problem becomes considerably more difficult because we don't know the dependence structure. And there's some assumptions. For example, if we assume the dependence structure can be modeled very well by, for example, a hidden Markov chain, then we have some results. We can solve this problem in a similar fashion and come up with a asymptotically optimal procedure. But in some more general dependence structure, how to model the dependence structure is a very difficult problem. For example, one needs to estimate the covariance matrix and so on. It's not so easy to solve that. And here are some papers. Thank you. David?
So there's a philosophical difference between what you're saying by using local FDR and the people who control FDR. So, you know, we've had several workshops in this 6-month period. And some of the people who spoke about FDR, what they're interested in is it's a the things like Benjamini, Hochberg, Symes's rule, and all of these, you know, that family of ideas. They're extremely simple to implement, and there really are very few assumptions. It's kind of very robust, and a relatively naive person can use them without getting into trouble, which is, let's say, a benefit. And in some of the some of the things that you've talked about, you're more ambitious in the demands you're placing on the abilities of the user to correctly apply the technology. But you didn't really, it wasn't completely clear to me what the user interface was, for example, in the group testing situation, what really the user has to be able to do and know in order to use your method. So that sort of user interface robustness is kind of a concern. Do you have any comments?
Yes, that's why we also provide software. And there's always a trade-off. And simplicity when simplicity is more important, certainly one prefer something that's simple but not optimal. But if you want to do well, or you pursue the optimality, you need to pay by understanding or by using a more complicated procedure. I think that's true almost for any problem. But by providing software, I hope that users don't need to know, for example, how to estimate those densities, for example.
Right, I understand providing software, and sometimes that works. Like, what does the user of this software have to know and do? That's what's going to come down to. It's not just can they download it, but they have to actually believe that they will use it correctly, and so on. Like, what actual demands are you placing on the user? What level of intelligence and persistence do they have to have?
I guess that's a hard question. It depends on the level of the user. For people here, I'm sure there's no problem. For a naive user,
you're presumably trying to reach out to people who are actually trying to do real multiple testing problems on a regular basis. That's what the benefit of the methodology ought to be apparent in.
I think based on the style of this presentation, I guess my sense is that for an average user, they need to know, assuming you know all the distributions, P0, F0, and F, then you know what's the property of the oracle procedure. And hopefully they don't need to know where those estimates come from, because that comes from a separate argument. But I think for an average user, they need to know that that's the case. For, say, a biologist, if they don't know anything, then they have to believe me. That's the optimal procedure to use.
On the last point that David raised, I have a paper in bioinformatics in 2006 where we do threshold on these posterior probabilities or on the local FDR, and we've got a program written in R called MXFDR, where we take 1 minus the p-value and then use a probit transformation and then fit mixture models to these z-scores or z-scores, as we'd say. But having said that, so I agree with you that you should threshold on these local FDRs and not the p-values, but in practice, you'd like the two results to be, you'd like the fact that, well, you'd like your local FDR to be a monotonic function of the p-value.
No.
Because, well, I think so. If I was testing for differential expression for genes in two classes, then if you perform an ordinary t-test and look at the p-values, I think in most situations you wouldn't want a sort of a pathological example that you gave on the board there.
That's the extreme case.
I think in most cases where you're doing studies of differential expression, you'd like the fact that the genes, whether you rank them in terms of the p-values or the posterior or the local FDRs, the rankings were roughly the same. But I think the advantage of working in terms of the local FDR, you get estimates of the false discovery rate or the false negative rate, and you could sort of look at those and choose the threshold accordingly.
I think whether those two procedures agree or not is not controlled by you, but by the nature. If the distributions are lined up, and those two procedures can be very similar or very close to each other, but there's no way that you can control that. Yeah.
Or robotics have that for a while.
I was going to comment on this. I mean, this is just the old story. I mean, when you're testing one-sided, then of course there's equivalence. When you're testing two-sided, if you assume that you've got symmetry of alternatives, then you get to the absolute value, and then you get this lack of equivalence. It's just a question of what do you think of as your alternatives?
No, not actually. It's not one-sided or two-sided, because here p-value based procedure, I mean that the one that based on thresholding the p-values.
Well, but the p-value itself refers to a family of tests, and if the family of tests is one-sided, then the p-value is equivalent to the observation, right?
It's equivalent to the observation, but it's not thresholding the p-values is not equivalent to thresholding the local FDR.
Yes, that's true. I'm not disputing that.
Okay.
In this particular case, I thought that the issue was more versus symmetry versus asymmetry.
Yeah, that also comes into play, because in one of the examples, it's exactly that case. Because if you take absolute value, you treat the problem as if it's symmetric. But if the true distribution is asymmetric, then you lose information by taking absolute value.
So, I mean, following Peter's point, it seems like you should, if you construct p-values not based on the absolute values, but on each tail, if you retain the sign of z, right, and you know the alternative asymmetric, I would think you should be able to get something similar to using the local FDR, right? Because
no, not if you thresholding the p-values.
But the p-value is not based on the absolute value of z. Now it's based on the sign z, right? So
Yes, but still, thresholding p-values is significantly different from thresholding the local FDR.
Can I make one more comment on that? I think the issue is whether you have whether you think that you have a monotone likelihood ratio family or not. If you have a monotone likelihood ratio family or not, then of course everything is equivalent. Of course, if you don't have a monotone likelihood ratio family, then sure, the thresholding is going to be different.
Yeah, I think that's a good point, but still there's some kind of sparsity going on. For example, if you just one signal at the magnitude 2, and you have a million of noise, so the signal is where it's not there. It's somewhere in the middle.
Yeah, so the point that was made earlier, I kind of, this non-monotonicity in your picture, if you had very, very strong prior information that when there was something going on, it happened at 1.5 and not at 2 and not at 3 and so on and so forth, then in a scientific setting, you could take the z-score and say, see, I got 1.5, right? And so that's my significant result. But it would look kind of strange in the scientific literature to selectively report not the best z-scores you saw, but something way down in the middle, and you selected that, and your audience, like referees, are going to say, well, where did that come from?
That's certainly true. That's why I emphasize that's an extreme case. It's not a typical case.
Have you looked at a case where the alternatives are not sampled from a distribution?
You mean they're discrete?
Well, just a list of p numbers.
Presumably it can be done, but we assume it has a density. Yeah, certainly that's an interesting case where you assume that an alternative comes from, say, a set of finite number of points.
Because then if I tell you one of the numbers, I've told you nothing about any of the other numbers. And the machinery seems to be based on learning something about the alternative distribution.
That's an interesting case, but I would assume that everything should still go through, whether the F1 is discrete or F1 is continuous.
So it's not just discrete or continuous. It's, you could have discrete things sampled from a distribution. I'm thinking of just a list of p numbers.
Yeah, that's exactly what I mean. You have, say, 1 minus p of F0 plus p of F1, and the support of this F1 is a finite set of numbers.
But I don't mean drawn from a finite support set. I mean a list where every gene has a number that if it's the alternative, that's what you get.
Okay, so actually that's the difference between using a random mixture model, and the so-called sequence model, where it's deterministic. Instead of drawing randomly from this group or that group, we assume we have, say, n observations. A proportion of them come from, say, this distribution, and another proportion of them come from this.
So we could even say we toss a coin with probability p, and if it's heads, you get the ith arbitrary number.
I don't think that makes a significant difference, although in this derivation we assume it has a density. Jamie?
Yeah, I've told you about this before, this great graduate student who independently did this kind of stuff, who disappeared into industry and never published it. But he did that model, and he showed that he control, if things are normal by a sufficiency argument, the statistic estimating f hat, f0, f1, and p by sufficiency argument, he showed he kept if everything was normal, kept the finite sample, FDR, under a completely fixed model. Power under the alternative, of course, depends on the model, in a sense. So I think the interesting question is, if the data was generated from this mixture model, would you have good power against that? I mean, the way frequentists usually think, but you'd like to know you protected whatever your version of the alpha level was under the non-random model. And that's what he showed using sufficiency with the normal case, which asymptotically would give you control, I think, in the same way from that model. And well, I'm going to make another comment about what David was saying. I mean, you yourself use things like thresholding and empirical Bayes all the time, where baseball players hitting higher than somebody else has had fewer at-bats. You pull them back more than somebody else. This is just, viewed from that point of view, this is just an example of that, except in the exact case you showed us from Robbins, not me, I wasn't born. He didn't uniformly, it wasn't like James Stein with the norm. He didn't uniformly beat the Minimax guy, he just beat it most places. But it's the same thing. That was thinking of fixed things being fixed, and it's just what parameter values do you win at? And you can win at a lot of them by using things like doing things that your average person or David Friedman, when it comes to the census, would think is crazy. Mixing up, if you want to estimate Chicago based on, Alabama, that's, you'd never like that, but you could prove under a certain loss function that was always as good by using James Stein, right?
As an intellectual, I agree completely. It's impeccable logic, etc. If I were a working scientist trying to get a publication of an important result to me, then the potential referee pushback to using a non-standard procedure would concern me, and that's
But David, everybody's always thought you think too small. In a few years, when Tony is God of the world. He's just going to say it's the right way to do it.
Don't say that.
You know, I mean, it's all sociology. Don't give up before we've lost.
Well, I just have a simple remark. When we talk about the discovery or non-discovery, we should address it to the scientists, not just among the statisticians. When you have a null hypothesis, it's essentially a statistical null hypothesis. So when you reject it, it does not necessarily mean that you have a scientific discovery. Therefore, when you see the empirical distribution of your p-value, even it does not follow the null hypothesis, which is uniform, it doesn't mean that you have a true scientific discovery you have in your mind.
Well, I think for biologists, this type of procedure is only for the purpose of screening. They don't really believe that this is significant, but they can spend more time and energy for further investigation.
Yeah. I've got an example from metrology that's close to your extreme case there. Measuring wind components, they are roughly normally distributed, but occasionally stations can't measure the wind for whatever reason, and sometimes instead of putting in missing data indicator, they put in 0, 0. And so we've got these normal distributions, and then there's a spike in the middle at 0, which we want to detect and screen out, but it's a problem.
I just want to make a comment regarding working scientists and et cetera. There is a circumstances which is not typical in biology, but in some areas involving signal detection, in which it would be routine for the scientists to do very intricate computer simulations of signals and non-signals and use those simulations to estimate your F0 and F1. In those sorts of situations, I think it'd be well worth taking a look at the kinds of ways that you're using them.
Okay, well, if there are no more questions, perhaps we could thank Tony again for writing them.